Alright, in this question we're told to find the strongest acid in this list. Which one is going to be the strongest? So what are we given? We're given the kind of acid that it is, the list. We're also given its Ka value. So what is Ka? Ka is going to stand for the acid dissociation constant. That A means that we're talking about acids. There's also a base dissociation constant, which we'll talk about later. That would be K to the B. Since we have an A, we know we're talking about acids. So what does that mean? The Ka, the acid dissociation constant, basically means how nice is that acid feeling? How willing is it to give up one of its hydrogen ions? So we know if we have a high Ka, meaning it's willing to give up a lot of ions, hydrogen ions in this case, that we're going to have a strong acid. So the higher that Ka value is, the stronger that acid will be. So we have this list of numbers, and we just have to find which one is the highest. Now an easy way to do that here in this example is just look at the exponents. Negative 11, that means it's going to have 11 zeros. This will have 4 zeros, this will have 8, this will have 5. That means that hydrofluoric acid is going to be the biggest of these numbers, making it the strongest acid. Alright, now in this question we're told that the pH of a 0.05 molarity weak acid is 3. And what we need to find out is the percent ionization. So for this question we're going to be utilizing the percent ionization formula, which will be the concentration of hydrogen ions over the concentration of our acid, which we can write as HA, at equilibrium. Take that number, it's going to give us a fraction, and then we multiply it by 100% to give us 100%. Now, let's see what we're given. We're given the pH. So we know that the pH is going to be 3. And we're also giving the concentration of that acid. So we write that as the concentration of HA, because we don't know what acid it is, 0.05 molarity. So we know what this is. Now what we need to find is the concentration of those hydrogen ions. And we know from previous examples that if we're given the pH and we need to find the concentration of hydrogen ions, all we do is we take 10 and we raise it to the negative pH power. In this case, it'll be 3. So this is our hydrogen ion concentration. So let's write the fraction and put our concentration of the acid underneath, 0.05, and multiply that by 100%. That should give us our answer. So if we do 10 to the negative third power, divide by 0.05, and then we multiply that by 100%, that'll give us our percent ionization of 2%. Alright, in this question we're told to find the pH of a 0.02 molarity HNO3 solution. Now the first thing that we have to recognize is that HNO3 is a strong acid. What that means is that when we dissolve it in water, it's going to completely dissociate to a hydrogen ion and a nitrate ion. So, what we can do with this information is see that the ratios are going to be 1 to 1 to 1. So there will be one hydrogen ion and one nitrate ion. And since it completely dissociates, we can take this concentration and understand that it will be the same once it dissociates for the hydrogen and the nitrate. Now, this is what we're going to look for, the hydrogen ion concentration. So that is what we need to figure out the pH. If we know it's 0.02, all we do is plug it into the pH formula. And as we said before, we know that the P in pH stands for negative log, and we just take that concentration of that hydrogen ion, 0.02, and we plug that into the calculator. Negative log of 0.02 will give us a pH of 1.7. And we have to make sure that this makes sense. pH is equal to 1.7. Now, this is a strong acid. 1.7 would be an acidic solution. So yes, that makes sense. 1.7 for a pH. All right, in this question, we're told that we have to find the pH of a 0.02 molarity nitrous acid solution. So this one's going to be a little bit different. So the first thing that we have to know, nitrous acid, is it a weak or a strong acid? This one's actually going to be a weak acid, so it's not going to be as simple of a process as the strong acids. In this question, we're going to be utilizing an ice chart, and you can watch the video on how to set up the ice chart that I have. So the first thing that we have to do is write out the equation. So it's nitrous acid, that is what we start with, HNO2, that's going to partially dissociate. That's what a weak acid means. It'll partially dissociate into hydrogen ions, and some of them will be nitrous. So, now we have to use this ice chart, and ultimately what we're looking for is to set up our Ka, our acid dissociation constant. We have to set up a formula which is going to be the concentrations of our products over the concentration of our reactants. So this is ultimately where we want to be. So we can start by filling this out. So we know initially that we have 0.02 molarity for nitrous acid, 0.02. And we're starting with none of our products. Now, for change, as our reactants move over to the product side, we're going to see a shift to the right. So we're going to write minus, and we're just going to put X. So we don't know what it is yet. And as the left side decreases, everything's going to move over to the right side. So this will be plus X, as well as this, plus X. And our equilibrium will just be the combination of these two. So if we start with 0.02 and we subtract X, that's what we'll get at equilibrium. So we'll just write 0.02 minus X. And if we start with nothing and we add X, then we'll just get X here. So what's important to remember about the Ka is that we're using the concentrations at equilibrium, the E in the ice chart. So we can write this out. We have the concentration of our products. Now, all these concentrations are going to be multiplied by each other. So if we take these two, it's going to be X times X, which we can write as X squared, divided by the reactants. In this case, it's 0.02 minus X. Now, what I forgot to mention is that we're given the Ka value, and we're looking for X. Now, we're told in this question, this is information given to us, that the Ka is 5.0 times 10 to the negative 4. So we're actually given the Ka. What we need to find is X, so then we can find the amount of hydrogen ions, the concentration of it, so then we can use that to find the pH. So what we need to do is rearrange our formula to get X by itself. The first thing we can do, multiply both sides by that denominator. So we can get X squared by itself. And then we'll multiply this times 0.02 minus X. You can rewrite this now as X squared is equal to 5.0 times 10 to the negative 4th times 0.02 minus X. Now, next, our simple math. Just distribute that 5 times 10 to the negative 4. So let's distribute it first to the 0.02 times 0.02. 5 times 10 to the negative 4 times 0.02. If we do that, we'll get 1 times 10 to the negative 5th. 1 times 10 to the negative 5th. And if we're multiplying this by x, negative x in this case, we'll just write, let's put this in parentheses, minus 5.0 times 10 to the negative 4x. And this is all equal to x squared. Now here, we're going to want to write it as the quadratic formula. So we'll get those ax squared plus bx plus c is equal to 0. So let's try and set this all to 0. So first thing we can do is add this amount to both sides. So to take that away from the right side. So if we add it to both sides, it'll now be x squared plus 5.0 times 10 to the negative 4th. Put that in parentheses so we're not confused. And we still have to subtract this from both sides. So minus 1 times 10 to the negative 5th equal to 0. So now we have our a, b, and c for the quadratic formula. A in this case will just be 1. This will be our b. That's right, b, a, and our c will be this amount. And we have to make sure that it's negative. So I'm going to put it into the calculator. I have a video on how to set up the quadratic formula in the calculator. So if we write a as 1, b as 5.0 times 10 to the negative 4th, and then c, we have to remember that it's negative. So negative 1 times 10 to the negative 5th. That's going to give us 2 x values. So if we erase all this, it's going to give us 2 because of the plus and minus in the formula. So it will give us x is either 0.0029 or x is equal to negative 0.0034. Now, how do we know which one to use? Well, let's just use our logic here. If we choose it, the second x, negative 0.0034, once we substitute it into that, how can we at equilibrium lose the products when we had none to begin with? So that's not going to make sense. Versus if we use 0.0029, we're going to end up with some products when we came from nothing. So this is the x that we want to use, 0.0029. And once we substitute that into our ice chart, we're going to substitute that into the hydrogen ion concentration. So we can write hydrogen ion concentration is equal to 0.0029. Now let's remember what we're looking for, because this is a long process. We're looking for the pH. This is exactly where we want to be, the concentration of hydrogen ions. Now, next thing to do is just to write that pH formula. Remember, the pH formula is negative log of our hydrogen concentration. We can write 0.0029. And once we put that into the calculator, negative log 0.0029, it'll give us 2.54. Is equal to a pH of 2.54. Final answer.
Thank you for watching. If you found this video helpful, or if you have any questions on what I should do next, please let me know in the comments below. Have a great day.